Hey, this is Jim Bergman with MeasureQuick. On behalf of AccuTools, we're here to do evacuation process, vacuum 301. If you're just getting started, there's actually 2 more videos before this, but let's get rolling on vacuum 301 and take you through the evacuation process. So there is a process for the fastest evacuation, and what I cannot stress enough is to keep the piping clean, dry, and tight. This means that when you're doing your brazing, you're sweeping that with nitrogen or CO2, and you've actually swept it the entire time, and actually before you ever pressurize it, we're also sweeping that because it's really, really important. I'll cover that in the next step up here. We're going to pressure test with only nitrogen or CO2. We never ever pressure test with air or oxygen. If we pressure test with air or oxygen, we could have other things like an explosion that we have to deal with. So always pressure test with inert gas. When we vent that pressure off, we're only going to vent it down to about 1 psi. So what we want to make sure is that when we pressure test, we take it down to about 1 psi. We do not want to let it go all the way down to atmospheric pressure because we don't want that moisture flowing back in. As long as there's a positive pressure in the system, we're pushing that nitrogen out, no moisture can enter in. We want to start with clean, dry vacuum pump oil. And my recommendation is always perform a single deep evacuation. I'll tell you a little bit about triple evacuation a little later on in the presentation, but there's no reason we need to do a triple evacuation. We want to pull below and hold the target for a thorough dehydration. We want to get that moisture out of the system. We want to isolate and verify acceptable levels and then document via a screenshot or report. So this is a really nice crisp pull down here. As you can see, we pulled that system down, and at about 5 minutes we were down below 250 microns. I isolated it, which is this little bump right here, and then when I isolated off, this is 20 minutes out. You can see that slow, small rise, and that's less than actually it's showing 0 microns per minute, which is 1 micron permissible rise. You can see we're nice and flattened out right there. So that's the type of evacuation we want to see. Vacuum pump oil, again, it's critically important. You want to make sure that you have a vacuum pump oil with a vapor pressure not greater than 5 microns at 100 degrees Fahrenheit. The pump cannot create a total absolute pressure deeper than the vapor pressure of the sealing oil. So oil is what's used really to create a big part of the vacuum. You cannot use refrigerant oil. If you're out of oil for your vacuum pump, don't pour in motor oil. Don't put in vacuum refrigerant oil. You've got to use a high quality vacuum pump oil to be able to pull a deep vacuum on the system. On small pumps like this, we should really change the oil after each use. On larger pumps there, you can actually change it less frequently, and you can use the ballast to remove moisture. But you always do want to change your oil on your pump, because even though we're pulling out and drive out a lot of the moisture, what we can't always get out are some of the acids and other things in those oils. Eventually the oil does go bad, it does need to be replaced. Pull out the valve cores. If you have a 6 CFM pump and you leave that core in, you just choked it down to 0.2 CFM. Even if you're using our True Blue hoses, you're going to choke that down there, because that core is a huge restriction to evacuation. With the core removed now, we're at 6+ CFM of flow, right? And that 6+ CFM depends on the level of vacuum we're at. And I think this is 6 CFM at maybe 100 microns on there. But you can see here when we pull that core out how much that opens that space up on that system. Use dedicated vacuum hoses. This one, again, really, really important. We talked a little earlier, these are the competitive hoses here. They've got pinpricks here. I've circled them there so you can see those. Pinpricking a hose cover permits trapped gases or vapors to escape from the hose carcass, right? I think it's called a carcass because this technology is dead. Steam, air, and other gases can permeate, pass slowly through the tube, and will build up in the reinforcement area. So the manufacturer must pinprick the cover on certain hoses. Now, why is this pinpricked? Because it's a repurposed charging hose. And guess what? If it leaks out, it also leaks in. And this is a huge problem. Freon charging hoses are charging hoses. Again, they're very gas permeable. We got all the oil to deal with. You don't want to use these hoses. They're way too small. We've already discussed that in an earlier video, but they're not the right type of technology in there. And it's really, really important that you use an engineered solution if you want to get the fastest vacuums and best results. Micron gauges. You've got to have a micron gauge, okay? You cannot determine proper degassing and dehydration using a compound gauge. You know, here, this is 0 to 30 inches of vacuum, right? Well, if you're looking at your inches of mercury, can you tell the difference between 29.14 and 29.916? No, nobody can see the difference on there, right? I mean, And that's the difference between 20,000 microns and 100 microns. You cannot tell the difference in there. You can't tell by the sound of the pump. You can't tell by time. You can't tell by pressure rise. You can't tell by pressure testing. You just can't tell how much moisture you've got in that system without a tool like a vacuum gauge. It's absolutely impossible. Remember, it's 2 steps: degassing, dehydration. So we're trying to quantify how much moisture we have in that system. You've got to use a good vacuum gauge to do that. When you're looking at vacuum gauges, I want you to look for the following: high accuracy, very, very important. We need to know where we're at in that vacuum. High resolution. Resolution means how much can we resolve. With this Pro gauge here, it can resolve down to 1/10 of a micron, okay? Temperature compensation. We want to make sure that we have a gauge that's engineered to work in the temperature extremes we work in. The old thermal engineering gauges were not temperature compensated, so they were good at 500 microns at 70 degrees Fahrenheit. That is it. You get away from that temperature, the gauge is no longer accurate. Leak rate indication. We want to know how fast is our vacuum decaying in microns per minute, because there's a permissible leak rate. Pull down indication, how fast are we coming down? Built-in diagnostics, is the vacuum gauge oil contaminated? Is it calibrated? Is it accurate? Field calibratable. Most of you guys never know if your gauges are accurate or not. You have no way of calibrating them. So you want to make sure you've got something you can calibrate. Factory rebuildable. These are not throwaway gauges and can handle high pressure. This gauge can take up to 1,000 psi. 1/10 of a micron resolution. It does have the pull down indicator, the leak rate indicator, the rise time indicator. You'll see gauges like this. This thing's got very low resolution, and it hides all the decay and it hides the leaks in the system. This thing's got 1,500 microns to 1,000 to 750, right? If I get down here at 500 microns and I'm watching the decay test, but from 500 to 750, I don't see anything. I have no idea if it's even doing anything. So this hides all of those characteristics, the things that we want to see in a vacuum, it hides. The old thermal one was really cool because with an analog needle, we could actually see the needle continue to move up or down there. But again, it doesn't have that temperature compensation, which is so critical to know how far in the vacuum that we really are. Avoid improper attachment. We already talked about small diameter hoses. We already talked about length being a big factor in there. Avoid refrigerant hoses. Avoid the manifold. You do not want to be connected here. I got a yellow jacket manifold. We're pulling through this. Absolutely the worst way you could do vacuum. This is tied in with a vacuum gauge in line. Again, reading at the wrong spot and using the wrong types of hoses. You want to attach it with a non-permeable brass connector like this one. Avoid connecting the vacuum gauge to the pump, right? Again, here we're connected to the manifold. I don't want to know what the vacuum is in my manifold. I want to know what the vacuum gauge is in my system. Here I've got a long 1/4-inch hose to the vacuum gauge over here, right? I got six foot of hose here tied to this vacuum pump. I can move that pump all the way up right to the system there and really make that hose much more effective on there, right? You'll see some pumps that have built-in micron gauges or roughing gauges. Okay, that's really cool, but only to see how deep the pump will pull. That's not a gauge to look at how deep your system is. Well, you can valve that off. You can look at how well the pump pulls, make sure it works. With a roughing gauge, you can't tell too much of anything, but it's okay to have that gauge on there as long as it's not your only gauge. And even a lot of the manufacturers have not gotten this right here. We're showing a 4-valve manifold system. We're connected through the manifold. Again, eliminate that. All this is excessive hose. We don't want to deal with that. And this is a ton of different leak points we have here. If a hose is loose or anything like that, we want to eliminate all those leak points on there. This is how you should attach your vacuum pump. This is a huge system. This is a 2,500 ton centrifugal. Notice that I'm doing the evacuation with a single hose on there, just one hose. Short, large diameter hose, valve cores removed, direct connection to the pump, core tools to isolate the system, gauges connected directly to the core tools, and vacuum rated hoses. Here's a residential system. I'm pulling from the high and the low side. Whenever we can, we want to pull from high and the low side. In this case, of this commercial job, it doesn't matter because the conductance speed of the system, the interconnecting tubing is so high that it'll pull down without having it connected to multiple points in the system. This one, I'm dealing with 2 small pieces of tubing, and I can pick up a little additional speed by connecting to 2 points in the system on there. Deep vacuum method. Evacuate the system to at least a depth of 2 times the allowable decay. So in this case, if my target's 1,000, I want to at least get down to 500 microns, right? 500 times 2 is 1,000 microns. 500 allowable decay, pull to 2 to 250. And ideally, what I'd like to see you guys start doing is pulling down to 100 microns or less, and that will create an adequately dry system. A decay test is used to determine the system's been properly evacuated, and a rise of 1 micron or less is generally permissible. So here you can see when I pulled this down, it leveled right off, okay? 0.0 microns per second a rise, that system's nice, dry, and tight. Here's a system that's wet and drying out. We pull it down, we isolate it, builds back up in vapor pressure real quickly. There's water in there. Those water molecules are expanding, occupying the full space of the container. It builds up really quickly. Pull it down again, it builds up slower. Pull it down again, it builds up slower. Pull it down again, it builds up slower yet. Eventually it passes here, right? Big difference on the two systems here. One is a dry system, one is a wet system, but both systems, and you can tell here, this took 1 hour and 15 minutes to dry out this system. 1 hour and 15 minutes versus 5 minutes to pull that down into a deep vacuum when it's not wet. You keep that tubing dry and tight, your evacuations will fly. You leave that thing wet and open to the atmosphere, you're going to take a longer time no matter what you're using. This one was really wet, it had actually standing moisture in it, but you get the idea of the difference there. Triple evacuation. This is often called the sweep, dilution, blotter method of evacuation. It's based upon using a dry gas to blot up and carry away the moisture in there. And this was used when the vacuum rig and the system could not achieve a deep enough vacuum to do the job on its own. This goes back to single stage vacuum pumps, okay? There's no reason we need to do this. It's a waste of time today. The first 2 pull downs were done at 27 inches. In fact, this is out of Carrier's guide right here. You can see they're showing inches of vacuum here. They're not even showing, at this point, microns of mercury because, again, this is older pumps, older technology. So here they pulled this down to 27 inches of vacuum. And then they waited 15 minutes at that range and then broke the vacuum and waited an hour. Pulled it back down again, 15 minutes, waited an hour, back down again 15 minutes, and then charged the system. So you can see here, this triple evacuation, you're talking about 45 minutes here and 2 hours. So 2 hours and 45 minutes to evacuate a system. You literally do not have to do that with one quick pull down on the system because I can get down to 100 microns in very short order, and I can assure you that system is nice, dry, and tight. Now, this is not a bad process if you have a system that you know is wet and there's standing water in there, because if we pull down really fast, especially on refrigeration systems, or it's winter time and it's cold out already, we could freeze moisture in the vacuum lines. This is very unlikely, if not impossible, for most air conditioning applications. You think about it, we're doing evacuation at 70, 80 degrees outside. There's so much heat in that tubing that it's gonna warm up that water as we evacuate it. It's gonna boil away so fast. Now, if we got into a deep freezing system where we had standing water, then this will help accelerate the time that it takes to get the system evacuated. But what you're really doing, this waiting an hour, is waiting for that water to evaporate, right? Waiting for the water to evaporate, and that's what we're using the nitrogen as gas to help carry it out. Nitrogen can only hold water vapor. It does not absorb it, right? So if we have liquid water in the bottom of something, we put dry nitrogen in it, the dry nitrogen is not going to swing by like a sponge and grab that liquid water off the bottom and absorb it. It just doesn't happen that way. It's a waste of time, though, on a dry system. So let's talk about that for just a minute on that water vapor. Let's talk about a couple myths that are busted. Now, air or nitrogen does not hold water vapor. We talked about that earlier. It doesn't absorb into the nitrogen. The water vapor simply resides in the empty spaces. So nitrogen acts as a carrier. When that water vapor gets in here and I blow that nitrogen out, I carry out some of the moisture with it. If there's any standing moisture in there, then it doesn't go anywhere. Now, we talked about also when air is compressed or cooled, the water molecules fall out because of the space between the molecules. This goes back to what I was telling you earlier, first part of the video, vent or sweep the system with nitrogen before you pressurize it. If there's a bubble of atmosphere inside that tubing, and we can press it down, right? It's just like this air compressor here. The water, the liquid will go from a vapor, it'll drop out in liquid. Once we get liquid in the system, it takes forever to remove. So we want to avoid that at all costs, okay? So very important to do nitrogen sweep first. And then again, the only thing that the water molecules can do is as a vapor, occupy the empty space between the nitrogen molecules. When we blow out the nitrogen, we'll carry out the water vapor with it. but if there's any liquid in the bottom, it's sitting there until it evaporates. When air is heated, the space between the molecules increases. Therefore, there's more space for the water molecules to reside. That's why we talk about hot air can hold more humidity than cool air can. And water vapor and air are two gases that are completely separate from each other. Some properties of moisture. We're going to talk about cohesion and adhesion or absorption. So the process of degassing is oxygen removal. It also causes what we call dehydration. Now here's the things you need to understand. Water sticks to water. That's called cohesion. And water sticks to stuff. And that could be stuff, could be like the inside of this tank here. And that is called adhesion. So water is adhered to the outer side of this tank here. If there's a little puddle of water, there's cohesion. The water molecules are sticking together, sticking to each other. Absorption happens right at the surface, right? And lowering the vapor pressure as we draw a vacuum on this tank, it's going to break these bonds of moisture away and it's going to start to dehydrate that tank. If we heat up the outside of this tank, it's going to help vaporize those water molecules away. A decrease in temperature, though, becomes a vicious cycle because as we start pulling a vacuum on this and this water in the bottom starts to boil, it absorbs heat from this tank. And as it absorbs heat from the tank, it gets cooler. As it gets cooler, it takes more and more space or more and more space up in the tank. We call this specific volume. Earlier, remember we talked about how the specific volume increases as the temperature goes down. The cooler this water gets, the more space it occupies. So this, again, is what causes that whenever we have water, standing water in the system, why it takes so long to get that evaporated out of there. How low should you go? Vacuum for service engineers, 1959, I think we said earlier in the video here, right? Old science. Finishing pressures of 1 to 200 microns are desirable to make this system, to make the air in the system so rare that there's only an insignificant amount of weight left for the refrigerant to absorb, thereby establishing good control over the subsequent head pressure of the compressor. Think about that for a minute. I doubt anybody here in general has pulled down microns to 100 microns as general practice. Yet that's where we should be going. Here's a system. This is a 5-ton system here. 99.8 microns, final vacuum, 99.8, 12 minutes and 19 seconds to get it down there. Comfort cooling new installation, we want to pull down between 100 to 200 microns. The copper should be dry, should be tight, this should be very, very easy, and we don't want to decay over 500 microns. And really this will flatten right out. You really won't get a decay much over 130 microns most time. Comfort cooling service equipment, 250 to 500 microns with 1,000 microns max. Now, when we're talking about service, where it's the system that's had refrigerant flow through it. We've already evacuated this once. Now we got refrigerant, we got oil, we got other things to deal with. We're not going to be able to pull that system as deep as fast. You know, a lot of times we're relying on the dryer, that we're cutting out the dryer and replacing it, put a new dryer in there. We're relying on that dryer to remove any residual moisture. General refrigeration, 100 to 200 microns, 500 microns max decay. Ultra low temp, 50 to 100 microns, decay 200 microns max. Again, what we're talking about now is moisture. When we get into that negative 40 on ultra low temp, we cannot let the micron level go up any higher. Some manufacturers will tell you got to be below 100. Some will tell you below 50, right? It all depends. When you get into ultra low temp, it depends on how far down you're going. Transport refrigeration, or things we see with mechanical seals, you don't want to pull much below 500 microns or 1,000 microns decay max. The mechanical seals just don't seal as well as a hermetically sealed system. Can you vaporize oil and damage the compressor? No. Okay, you just can't do it. You can pull out moisture, you can pull out gas, refrigerant gas, but you cannot vaporize the oil even at 30 microns. The vapor pressure of refrigerant oil is far too low. When you see bubbling of the oil, it's typically emulsified refrigerant or emulsified moisture. It's mixed in with the oil and we're just boiling it out of there. But it's not the oil evacuating. Manufacturers consistently pull down into the 100 micron range when they're doing this kind of stuff. I've seen systems down as low as 30 microns and the oil looks just like this, just as still as could be. We're not going to evaporate the oil in the system. That is an old wives' tale. It's bad information that came across the industry. When we do the isolation, this is isolate the decay test, okay? There is actually a standard. Again, the review of vacuum for service engineers. The permissible pressure rise is generally set at a raise of 1 micron per minute. with a finishing rate of 1 to 200 microns desirable. I'll click this video here. You can see it, we're opened up. We start closing that valve off down in the bottom. We're at 135. The micron range is rising up to 153, 157, 160. This is a decay rate we're looking at. And eventually that's going to go up very quickly, and then it's going to flatten out, and we can see what our ultimate vacuum is. So we're testing the tank now to see how far down that has held and what the actual vacuum is. You cannot test vacuum on a system unless you isolate it. You have to close the core tools off and actually see what the evacuation is, right? Also, with the app here, I'll show you the app here in just a minute, it takes the mystery out of evacuation. You can't tell on a standard vacuum gauge whether you have moisture or a leak. And TrueBlue is one of the only systems with the BlueVac Pro that you can actually do this. What we've done here is we pulled down, we're down here about 400 microns or so, and we isolated off. You see this straight up rise and then this continual rise. This is indication of a leak. This is over time. So the only reason this is at a small angle here is because it's over time. If we took the time factor out, this would literally be going straight up. It'd just be a straight up leak, okay? Now notice here we pulled down, we isolated, and it tails off. Tailing off means that the vapor pressure is gradually building up. It gets to the point where the vapor pressure equalizes in the system. This is right about 2,500 microns, so this is a good indication of moisture, 2653. So you can see here, this has got a decay rate of 42.7 microns per second. After this is stabilized here, this is looks like about 8-9 minutes, the decay rate is at 0.8 microns per second. So this is not continuing to rise, it's leveling off. With that, it's just a continuous leak. So it allows us to stop moisture in its tracks. After you're done, you're going to document the job well done, right? We can pull this down, we can generate a report. It's going to show us the total elapsed time, the time to ultimate pull down. It's going to show us where we pass, fail, what our ambient temp was when we're doing the evacuation, our final vacuum where we isolated off, and then the device serial number that we're using here. And this is really, really good way to document your evacuations. So now I want to get in here and talk a little bit about the results, way faster evacuation times and longer system life. This is a 2,500 ton York chiller at the University of Kentucky. There's a video that Andrew Greaves and I did on this. This thing is about the size of 2 buses. I mean, it's a huge, huge chiller here. About a 30-inch suction elbow. Evaporator and condenser lengths are, like I said, about the length of a school bus. Typically, they would take 4 to 6 days to perform this evacuation. We started this at 4:30 in the evening, and we came back the next day. We thought we'd be down, so far we didn't have any idea. But we did that with a single 3/4 inch hose in about 17 hours. And how far down did we get? Well, one hose, 12 CFM at the pump, no oil changes. We literally started overnight. 121 microns at the pump, 314 microns at the far side of the system on there. So you can see, 121 microns down here at the vacuum pump. We put 2 gauges on there so we can see our pump performance. Put another gauge on the far side of the system so we could see. You can see me standing next to this thing so you get an idea how big it is there, how physically big. 12 CFM NAVAC pump here, connected with 1 port directly to the system, and we got that system down sub 300 microns in, again, 17 hours. Residential system, this is a 100-foot, 3/4, 3/8 line set, existing line set. Cleaned it with R11 flush, so this was a replacement job. It had a 4-ton evaporator coil, 8 CFM pump, 5 minutes. Did less than 200 microns on that system, 5 minutes, start to finish, right? So again, what would normally take that contractor an hour to do, we got done in 5 minutes. So a substantial time in the savings in the evacuation. Oxygen and moisture are the absolute enemy of a system. Oxygen's an oxidizer. It's going to cause corrosion. It's going to cause things to get eaten up. It turns the oil black. In this system here, you can see all this black gook in here, and that's all oxidation. It's oxidation of the oil, the hydrocarbons, and it can actually vaporize the motor windings in here. This is where we get a bunch of nasty stuff. If you leave oxygen or moisture inside of a refrigeration system, it's like a miniature chemical plant. It's constantly manufacturing acids and sludge and all kinds of gook that's going to just ruin that system. Plus, these acids are so powerful that they actually strip away the copper that's on the line set and redeposit it on the bearings there, right? So that acid stripping redepositing is what causes the compressor to get tight. It's what causes things not to work right. Dryers can help a little, but the destruction is continuous. So you want to get all that moisture and oxygen out on the front end of the system. Internal formulary corrosion of copper. This is also called ant nesting. There's only a couple things that cause this. You've got to have oxygen, you've got to have moisture, you've got to have copper, and you've got to have organic acid. If you have those substances out there, you're going to get this, you could get this formulary corrosion on there. This is showing it from the outside in. It can also happen from the inside out, and it's typically found in copper and copper alloys. And then once you get rid of one of these components, if you get rid of the oxygen, the water, the copper, the organic acid, the formulary corrosion stops here. So if you want to avoid that from happening from the inside out, a good evacuation is the way to do that. What I've got here, I've got a 5-ton evaporator coil, and I've got it hooked up with 50 foot of 7/8 tubing and 50 foot of 3/8, so a 3/8 by 7/8 line set. I've got it hooked up with our True Blue hoses. I've got this line here, it goes, it's a 3/8 line, but it goes right to the 7/8 tubing on the far end. And then I got the 3/8 connected over here. So we're pulling on both sides. I've got the micron gauge hooked up at the evaporator coil, right at the outlet of the evaporator, so I'm about as far away as I can get from there. I've got this system wide open. I got the cap off here, so I'm going to go ahead and cap that, and we'll go ahead and do a pull down here, and let's show you how fast that we can do this as we go. So there's a few things here. I'm going to actually start out, I'm going to go back here and restart the recording, and then I'll kick on the pump here. So we're at 760,000 microns. We're at atmospheric pressure here. So the pump is a DC pump, so it's got a soft start. So you heard that start a few seconds after I did the switch. That's getting up and running here. And in a few seconds here, now remember we're at 760. Now we're just down to 120,000 microns, 48,000 microns, 29, 25. Now remember I told you before, all that traffic, 760,000 microns, we had a huge amount of air density, and how it was only going to take a few seconds. We're at 30 seconds in, we're already at 6,000 microns. So those quarter-inch ports, they aren't even a factor, right? Because we've pulled down so fast, so far beyond that, that those aren't a factor anymore. So now we're down to 2,000 microns, 43 seconds in. Let's look at the graph on here. The graph we're pulling down, you can see how quickly this is coming down here, 1,800 microns. This system is very nice and dry, so we're going to give this a couple seconds here. I'll let this go all the way down until we get 100 microns on the evacuation. Now on the app here, what we're showing here is a couple different things. Up at the top here, this is a lot of oxygen and a lot of moisture. So this is the red range. This is where we want to be out of. We get into this portion down here, it's starting to dehydrate. And then down here in the dark green section is where we're really nice and dry on there. On the gauge, we're showing you a couple different things too. The ambient temperature in here is 75.3 degrees. Our pull down is 13.1 microns per second. We can also do that in microns per minute. I can go in here, I'll change the settings on here so we can see this decay in microns per minute. So we'll scroll down to the bottom here, app settings, gauge. And we'll change this to microns per minute. We'll hit check on there. So now we're at 430 microns per minute. So we have a really, really fast pull down here. We just crossed 500 microns. We crossed 500 microns at 1 minute and 45 seconds in there. So literally 5-ton system, 50 foot of 3/8, 7/8 line set, and in 1 minute and 45 seconds we're down to 500 microns, and you can see we're still going at 239 microns per minute on our way down to 100 microns. This is our saturation temperature. This is the boiling point of water. We're at negative 23 degrees. So again, this system is really nice and dry, and we're coming down quickly on that. We'll give this a couple more minutes to come down. The graph here, when it hits this point here, it's going to rescale. So we saw it rescale there, and we're still on our way down. Now, in the front of this, if we go back to the home screen on here, you can see we got a target here. This is our final finishing vacuum. So you can see this is coming down. We're in a dry section here. We're at 266 microns. We're in a dry section. We're approaching this target down here of 254 microns. So let this keep coming down here. A couple more seconds, we'll be down, and we'll be good to go. All right, so we're down to about 110 microns. You can still see we're pulling down at about 23 microns a minute. We're going to be down here at 100. And again, I want to be at a finishing vacuum of 100 microns. Let me just scroll through ahead here so you can see here. We are 5 minutes and 53 seconds. So in 6 minutes, we got a 5-ton system pulled down to 100 microns here, which we probably crossed at this point now. And there we are at 102 microns. 101 microns. So I am down. This is as far away again as I could get from the pump. So I'm at 100 microns right now. I just crossed it. You hear my gauges beeping here. So I'm going to go ahead and it's telling me it's time to isolate the system. So I'm going to close these two valves off here. And when I close those two valves off, I'll just go ahead and kill my pump. And now I'm going to hit continue. And I got the system isolated at this point. Now it's telling me again now that I've got a pass here. I got pass on my gauge. And it's showing me pass on my gauge because it's calculating out what the decay would be. So you see a very, very tiny rise right here when I isolated this out. In fact, I can zoom in on that if you want to see that a little closer. So I have a very, very tiny rise on there, and this is starting to flatten out. Now there is a rise rate here, and right now it's at 11 microns per minute, but it's telling you that based at this speed that it's going to slow down or decay. The decay is going to taper off to a point where it's not going to matter. Because we have this set up so that it's going to in the app automatically to tell it to pass decay once it hits a certain point. So this will continue to rise up and slow down, and once it slows down and drops off here, then we'll know that, that the system's passed, but otherwise the gauge has told us already that it's passing. You can see this is flashing between 10 and 11 microns per minute, and eventually that's just going to rise off and flatten right out again. But this decay part, what we're doing, we're waiting for that system because the pressures at each end of this tubing are much, much lower than they are at this gauge. So we're letting that pressure sort of equalize out. And as it equalizes out, that's what the decay time is. So now we're down at 10 microns per minute. If we let this go for 10, 20, 30 minutes, we'd see that would taper off to 0 microns per minute like I've shown you in the other parts of the video. So that gives you a really good idea here of what that looks like. We'll zoom back out so you can see how flat this line is here. So this is definitely going to flatten out. We're not going to get to this 500 micron mark anytime soon. You'll probably go out a couple of hours, and eventually it's just going to reach out and just flatten out and it won't even rise anymore. But you can see now we're down to 9 microns per minute of rise, and that's our permissible rise rate is 1 micron per minute, but we can tell automatically with a gauge timer when this thing is, with a gauge programming that it's right there and done. So anyway, this gives you an idea of what we're going to do. In the last part of the video here, I'm just going to do some additional notes, and then we'll wrap this series up.